Okay, so now we're going to keep working with differential equations, moving on to section 8.2, which is constant coefficient linear differential equations. So long title. Really all this means is that, if you remember from last video, we defined this L here as some sort of linear differential operator that just, gives you a linear combination of all of these individual differential operators here, all these D's to different powers. And then the main distinction here is that in last video, we said that these constants here don't necessarily have to be just numbers, right? They could be functions of x, and we actually did an example, and you even had some on your homework where these constants were actually functions of x, okay? But what we're going to do in this video and moving forward is that these are going to be just numbers, okay? And so we just define P of D, now another definition, is a linear differential operator. So it's exactly like L. With constant coefficients. So we say that, to write this more mathematically, we say that the set of A1, A2, all the way up to AN are constants, okay? Just real numbers. And then we just, give this special case a name, P of D, okay? And so what you're going to do to actually solve differential equations is you're going to, first of all, you're going to have to convert the differential equation that they give you into something that looks like a polynomial differential operator, and then you can go through and do the methods they talk about in the textbook, okay? So the general methodology here, so you're given some differential equation, y double prime plus by prime plus cy is equal to 0, okay? So again, B and C are just going to be numbers here. What you do is you first convert it to a differential operator, P of D. And then what you do is you find its auxiliary polynomial. We'll talk about what that is in a second with a few examples. Those steps 1 and 2 are really arbitrary, you'll see in a second. Once you have this auxiliary polynomial, you factor it out, and then you're able to find its roots. So you find the roots of the auxiliary polynomial, which I'm just going to call r sub I. And then once you do this, your solutions will involve our friend, the exponential, okay? E to the RIX. How exactly these solutions will involve them will depend on a few cases, which we'll talk about below. But this is just a general methodology here. And with some practice, you should get the hang of it. So this is going to function a lot like the lecture that was given in terms of second order differential equations, but I wanted to just spend some more time on it so you get a real solid foundation as to what's actually going on here, because I don't think the textbook does a particularly good job in section 8.2. Okay, so let's go ahead and work with the first case here. So as an example, we have y double prime minus 5y prime plus 6y is equal to 0. And they want you to go ahead and find the solutions to this differential equation. So what we do first is we convert it to a polynomial differential operator. So we just write we write y double prime as d squared y, as we've seen. We write 5y prime as just 5dy, and then the 6y, there's no derivatives involved, right? So we just add 6y to it to give me 0. And then this is where, having this, like the format here actually helps us out quite a bit. So we can factor out the y and pretty much resolve this out to this is now our polynomial differential operator. Okay. What we do now, we've done this. Whoops. We've done that. Now we need to find the auxiliary polynomial. There will not be an easier step in any mathematical process than this, okay? What you do is you replace the d's with r's, okay? So now you have r squared minus 5r plus 6 gives me 0. You ignore the y, and this right here is my auxiliary polynomial, okay? That's all you do. So 1 and 2, right off the bat, pretty simple to do. And you'll get the hang of it real quickly. Now what we have to do is we have to factor this auxiliary polynomial down as you would do in any algebra course. So you have r minus 3 and r minus 2, right? Give me 0. So I know immediately that one of my roots, r1, is going to be 3, and then r2 will be 2. Great. So I found my roots of my auxiliary polynomial. What do I do here? Well, notice that they're distinct, okay? So I have distinct roots. They're not the same. So the textbook, and it's just going to be like an algorithm here, says that corresponding to my first root, I have one solution, which is e to the 3x, okay? Corresponding to my second root, I have another solution, which is e to the 2x. You can show that these are linearly independent, but what you've done then is you have two solutions here. They're linearly independent, and then you had in the beginning a second order differential equation. So you're done. You found two linearly independent solutions to a second order differential equation. You have your solution space. So you can then write a general solution to this differential equation as just a linear combination of those two. So some constants like this, and you're done. This is your solution here, okay? So notice how easy this was because we had these distinct roots. So in this next example, it gets a little trickier, but not too tricky. So let's take now y double prime minus 6y prime plus 9y gives me 0. So converting it to my polynomial differential operator, this becomes d squared y minus 6dy plus 9y gives me 0. So d squared minus 6d plus 9y gives me 0. So there's my polynomial differential operator. My auxiliary polynomial pops out of that, exactly like this. Boom. It's just really all a formality. If you can see, all we're doing is just pulling the coefficients. So if you're running out of time in an exam, just, do that. Then we can factor this out. So this factors down to r minus 3 squared gives me 0. So I have one of my roots, r1, gives me 3, right? My second root is actually 3 as well. So I just say it repeats twice. Cool. Okay, so if we scroll up to this previous example, if we have a root here, we know one of our solutions is going to be y1 of x is e to the 3x, okay? But, you might be stuck here because you're saying, okay, well, I have in my beginning here a second order differential equation, but I only know how to find one solution here. And so there's some fancy stuff done in lecture and also in the textbook, but what you need to know on exams is that to find your second solution, all you do is you multiply it by an x, okay? So you take your first solution and you multiply it by an x, and out pops your second solution here. So your general solution to this differential equation then is just a linear combination of those two. Again, if you want to know where this x came from, the professor did a good job of explaining it in lecture, and you're welcome to take a look at that. So here, you're done. These are linearly independent solutions, so their linear combination gives you the span of the solution set here. Okay? And the last case, the case everyone hates. Let's do an example of it. Let's do y double prime plus 8y prime plus 20y is equal to 0. Okay, so again, let's do that auxiliary polynomial stuff, just so everyone's really clear about it. D squared plus 8d plus 20 applied to y gives me 0 is my polynomial differential operator, and then my auxiliary polynomial is this. Okay, so notice in the previous examples that we could factor this out with no problem, right? We knew right off the top what our r's were going to be. But here it's not so trivial, right? So what you have to pull out our old friend, our really old friend, the what's it called? The quadratic formula. How did I not remember that? But we have to pull out the quadratic formula here to find our roots. So it's negative b plus or minus the square root. I never learned the song. B squared minus 4ac over 2a gives us this. So we can reduce this. R is going to be equal to negative 4 plus or minus. In here, I have the square root of negative 16, which we know is going to give us plus and minus 4i. So I get plus and minus 4i divided by 2 gives me plus or minus 2i. Okay. So I have R1 is negative 4 plus 2i, and I have R2 is equal to negative 4 minus 2i. Okay? So there's nothing wrong, right? These are distinct roots. I'm not running into any trouble here. And so we know if we have distinct roots, then my first solution is e to the negative 4 plus 2i times x. And then my second solution is e to the negative 4 minus 2i, the whole thing multiplied by x. And technically, yes, we have found two solutions to our differential equation. But nobody likes this form. This form sucks. So what we want to do is we want to play around with the rules of exponentials and see a little bit of Euler's formula here to help us break this down into, equations that actually make sense to us, okay? The other thing is we have these i's in here, and we generally don't want to have imaginary solutions here. So we need to get rid of them. So what we can do is we can use Euler's formula, which you saw in lecture. And so what this says, e to the aix. Okay, so I have some exponent. It has a complex part to it. I can write this out as cosine of ax plus I sine of ax. Okay, so this is just a definition. Some genius came up with it, and we accept it now. It's pretty cool. It has cool properties and stuff. But what we're going to do is we're going to use it to kind of reduce y1 and y2 to make them prettier. So let's look at y1 of x then. That's equal to e to the minus 4x times e to the 2ix. So just by using properties of exponents, I can break the two of them up into this product. So this is times here. The e to the minus 4x is fine, but now you can see this looks a lot like Euler's formula here. So I can rewrite this out, e to the minus 4x, and then the only thing that changes is a becomes 2. So I have cosine of 2x plus I sine of 2x. Great. We can do the same for y2 of x. Is e to the minus 4x here. And then times e to the minus 2ix. So again, just broke it apart. And I'm going to use Euler's formula here with a is equal to negative 2. So I get cosine of negative 2x plus I sine of negative 2x. And this, last important part here is that I want to get these negative signs out of here. I don't really like having negative signs inside trigonometric functions. So I know cosine is even. So cosine of negative 2x is the same as cosine of 2x. And then sine is odd, so I know that sine of negative 2x is negative sine of 2x. If that was quick, just brush up on even and odd functions. And this is what we get, okay? So we have two solutions here, right? And you might say, Jimmy, those look way worse than what we started with. And I would agree with you. So we started off with these exponents here, two solutions, fine. We decompose them into an exponent here times sines and cosines, and we still have this I hanging out. So what we do now is we actually start taking linear combinations of y1 and y2, and we see if some stuff will cancel out to make them even prettier, okay? So you saw this in lecture, but what we're going to do is we're going to first add the two of them, y1 of x plus y2 of x, and we're going to divide it by 2. So take my word for it for now, and we'll see what actually happens here. So if I add y1 to y2, I can factor out this e to the minus 4x, right? And then I'm adding, let me get rid of some of this green stuff here first. Get a clean slate. I'm adding this cosine here to that cosine here, which gives me 2 cosine of 2x. And then I'm adding this I sine 2x to this negative I sine 2x, so they cancel out. And then what I have to do is just, divide it by a half. Great. So then one of my solutions, just by playing around with it a little bit, we get e to the minus 4x times cosine of 2x, which should look familiar to you from lecture. Okay, and we do the exact same thing with a different combination. So we take y1 of x, this time we subtract y2 of x off of it, and then we divide it by 2i. So now our goal is to get rid of the cosines and leave the sines. Okay, so again, the e to the minus 4x is common, so it comes out. And now I am taking this cosine up here and subtracting off this cosine, so they go away. And I'm taking this I sine of 2x and subtracting a negative I sine of 2x. So this becomes 2i sine of 2x. And then by definition, we just, divide by 2i here. So then my second solution is e to the minus 4x sine of 2x. And boy, do those look a lot better than what we started with, okay? So we have some we have some exponential term and a sine and a cosine. That looks a lot better than this, and it certainly looks a lot better than what we had here, okay? So you don't need to do all of this every time. I'm just showing you where these things come from. What we can do now is we can start to generalize this to just a base case here of 2 dimensions, okay? So we had 3 different cases that popped out, if you remember, 15 minutes ago. So in general, we have y double prime plus by prime plus cy gives me 0. You have a few cases. So the first case, call it case 1. That's not even close to spelling case. All right, case 1, you have 2 real distinct roots. So they're not the same. That was, let's scroll up a bit here, this case here. We saw it was super easy. We just plug them in as our solution, okay, to to our exponential terms. So we know that y of x, I'll call these R1 and R2. Y of x then is just a linear combination of these 2 exponentials. So we just stick the roots up into these exponentials and we go from there, okay? There's our first case. Case 2, we saw we can have 2 repeated real roots. Okay, we'll just call it R1. That's repeated twice. And we saw in that case, I'll scroll up again. It was this one. If we have a repeated root, we just have to stick that extra x term in there. So we have y of x is equal to c1 e to the r1x as normal. And then we have C2xe to the R1x as well. That's our second solution that pops out. And then case 3, the very last one we did, we have two distinct complex roots. So I'm going to call R1, let's see, what did I call it? Alpha plus beta I. And then we saw that if they're from the same quadratic formula, the other one you get is alpha minus beta I. Okay. And then we didn't really talk about this, but these numbers here, this -4 and this 2, were familiar, right? They came from what we put in the exponential, and we go one step back, what we actually got as our roots, okay? So it's all related. Our solution becomes, what you do first is you take linear combination, so I need a C1. What we saw go into the exponent was the real term, my alpha here, and then I multiply it by cosine of beta x first. And then my second solution was e to the alpha x as well, and then multiply it by sine of beta x. Okay, so these are the three possible cases you can have, and I'll stress this is when working with a second order differential equation, okay? But the cool thing is, and what the professor was stressing, is that this actually generalizes a lot to higher order differential equations. So if you want to go through, and I think it's good practice actually, section 8.2, you'll see actually that these cases generalize, and you follow the same formulas for them. By sticking in an x if you have repeated stuff. If you have stuff repeated 3 times, you stick in an x squared instead, and so on and so forth. But I just wanted to cover the few base cases so you get a good understanding of what's going on.